Well, to continue with our discussions on non-ideal solutions, before I proceed for today's class, I would just have a short recap of what we have already done, just taking into consideration the fact that non-ideal solutions are quite complex. Means when students first deal with them, they often try to get confused with the different sorts of terminologies, one extra set of properties that have come up. So, I will have a quick recap of what I have already taught in the last class, and then we proceed further. What did we do? Initially, when I started solutions, I dealt with ideal solutions. I would like to mention I had dealt with two types of solutions. One was ideal solution, one was ideal dilute solution. Most of my discussions are limited and will be limited to ideal solutions, and maybe at some times I will touch upon ideal dilute solutions. And therefore, did we find again as a recapitulation, we found out that more or less the Lewis-Randall rule is applicable for ideal solutions, where we get that the partial fugacity of component I in a solution, it can be a vapor mixture, it can be a liquid solution, does not matter, the law is the same. This is equal to xi fi. If this refers to a liquid solution, it can be denoted by a superscript L, and if it is a vapor solution, then it can be communicated it can be represented by a superscript V, right. And we found out that under equilibrium conditions, FIL equals to FIV. So long our situation was fine, and then we found out that the situation becomes simpler at low to moderate pressure. Why? Because under those conditions we found out that the Lewis-Randall rule, it reduces to Raoult's law. Reduces to Raoult's law. As a result, what do we find? We find that the F's can be replaced by P's, the pressure terms. As a result of which we find that for low to moderate pressure, it becomes Pi equals to Xi Pi saturated, and in this case Pi equals to Yi P. Okay. Recalling that for the vapor phase at low to moderate pressure, or in other words limiting P tends to 0, F of pure component of the vapor phase, this is the total pressure if you recollect. And for the liquid phase, what did we derive? We derived for the liquid phase, this was equal to P saturated, and then there was some other correction terms taking into account the corrections which would account for the non-ideality of the vapor phase, as well as the compression of the liquid from the saturated pressure to the pressure of interest, which was incorporated in an exponential term often termed as the Poynting correction factor, right. So, therefore, for low to moderate pressure, this was the situation, and this is the rule according to which we can write down, we can combine the two, and we can write it down in this particular form for an ideal solution. Then we went for a non-ideal solution. In a and according to this, we also found out that if we plot pressure versus x1, then in that case what do we expect? We get the total pressure curve as something of this, the P2 versus x1 curve like this, and the P1 versus x1 curve in this particular fashion. We found that all the three, they are linear, because partial pressure of component 1, partial pressure of component 2, as well as the total pressure, all of them vary linearly with the mole fraction of either of the components. It is important to remember that when we are plotting these phase diagrams, we are always plotting the mole fraction of the more volatile component in the x axis. It can be the mole fraction of the more volatile component in the liquid phase or in the vapor phase, but just by convention we try to maintain the fact, or that maintain the practice that we will be plotting the more volatile component composition in the x axis. You will often come across problems, maybe I can also give you can get such problems in your in the textbooks which you are referring, and you will find that in those problems often we find that the less volatile component composition is used in the x to plot in the x axis. It is interesting to remember that the curve remains same only when we are plotting the less volatile component. Quite natural, its vapor pressure will be less, as a result of which under that condition what are we going to get? For that condition, if it is x2 or y2, then in that case we will be getting something like this. The curve will just change, because it is important to remember that the less volatile component will have a lower vapor pressure as compared to the more volatile component. This is the only thing which is going to happen, right. After this, what we did? We went to non-ideal solutions, and in non-ideal solutions what did we find? We found out that in non-ideal solutions there can be either positive deviations from ideality or there can be negative deviations from ideality. Okay. When we have a positive deviation from ideality, the total pressure calculated is greater than that calculated from Raoult's law. When there is a negative deviation from ideality, the total pressure calculated at any particular composition is less than that predicted from Raoult's law. As a result, it was felt necessary to modify the equation which we had derived, this equation or this equation for ideal solutions, in order to incorporate non-ideal behavior, and this was done by introducing a term yi in the gamma I in the equation or the Lewis-Randall equation. And for low to moderate pressure, what happens? The equation reduces to Pi equals to gamma I xi Fi liquid if it is a liquid phase. And it is also important to remember that mostly non-idealities they exist in the liquid solutions. Gaseous mixtures are usually ideal. Why? Because the Lewis-Randall rule is based on Amagat's law of additive volumes, which I have mentioned several times in my previous classes. So, therefore, for non-ideal solutions we find that the non-ideality is taken care of by introducing this particular activity coefficient in the Lewis-Randall rule. And we found out that once we can find out gamma I, then the Rayleigh behavior of non-ideal solutions and ideal solutions are naturally the same. The only difference is that in this particular equation we will be having a gamma I here, there is now no other change. So, therefore, we have introduced one other property of component I when it is in solution. So, the next interest was to express gamma I in terms of known parameters or in terms of parameters which we have already discussed. In the last class we have made those particular derivations, and we found out that the ln of gamma I, it is nothing but equal to the partial molar excess Gibbs free energy of component I in solution, right. We also found out that the variation of gamma I with temperature can be related to the partial molar excess enthalpy of component I in solution, and its variation with pressure can be related to the partial molar excess volume of the component I in solution. So, this was what we had derived in the last class, and after this what we did was we derived the Gibbs-Duhem equation in terms of activity coefficient, and I stopped there, mentioning that particularly for binary solution the Gibbs-Duhem equation gives us a large number of important information. So, let us start from that particular point and see what are the important informations that we have. Okay. So, therefore, I believe I had derived, or rather we had derived this particular generalized equation, Gibbs-Duhem equation, in terms of activity coefficient, and this was the equation which we had derived, and in this particular equation at constant temperature and pressure, naturally this becomes 0, this becomes 0, and this is the Gibbs-Duhem equation, which for a binary mixture reduces to this. Now, let us see what important information we can get from this equation. Say for instance, if I write it down as, I will just write it down and derive it once more, x1 d ln gamma 1 plus x2 d ln gamma 2 equals to 0. Can we not write it down as x1 del ln gamma 1 del x1 at constant temperature pressure plus x2 del ln gamma 2 del x1 at constant temperature pressure, this is equal to 0, or in other words del ln gamma 1 del x1, is this not equal to minus x2 by x1 del ln gamma 2 del x1 at constant Tp? We know that since it is a binary mixture, dx2 equals to minus dx1. So, this can be written down as minus x2 by x1 del ln gamma 2 del x2 at constant temperature and pressure. Automatically, what do we see? We see that the first thing is slope of ln gamma 1 versus x1 is just opposite to the slope of ln gamma 2 versus x1. This is the first thing that we see here, right? Number 1. Number 2, can we write down this particular equation? So, let me write down the first thing, slope of ln gamma 1 versus x1 opposite to slope of ln gamma 2 versus x1. What is the next thing that we know from here? We know that as x1 tends to 0, what happens, you tell me? X1 tends to 0 means x2 tends to 1. Naturally, under that condition, what happens? Your gamma 2 tends to 1 and ln gamma 2 tends to 0. So, therefore, what do we see? We see that when we are plotting gamma 2 versus x1, then at x1 equals to 0, the gamma 2 becomes equal to 1. And similarly, we also see at x1 tends to 1 or x2 tends to 0, what happens? Gamma 1 tends to 1 and ln gamma 1 tends to 0. Quite natural, whichever component is in x's, it is natural that gamma 1 and gamma 1 tends to 1 at x1 tends to 1 and gamma 2 tends to 1 at x2 tends to 1. Fine. Achha, what is the other thing that we can observe from here? Just observe and see from the equation which I have written down. The equation implies that let me write down the equation d ln gamma 1 dx1 constant Tp, this is equals to minus x2 by x1 del ln gamma 1 del x1, right. Now, or in other words, if I write it down in this way also, x1, can I not write it down as x1 by gamma 1 dx1 d gamma 1 dx1, is this not equal to minus x2 by gamma 2 d gamma 2, sorry, these are all gamma, very sorry, d gamma 2 dx1. Can I not write it in this particular form? I can write it down, or else I can also write it down as, in this form also I can write it down that 1 by gamma 1 d gamma 1 dx1, is this not, because what happens, is this not equal to 0 at x2 tends to 0 or x1 tends to 1? What does this imply? It implies gamma 1 versus x1 has a horizontal slope at x1 tends to 1. Fine. So, therefore, there are 3 observations which we find from here. What are the 3 observations? The first thing, if you observe the equation, this particular equation, what do you find? number 1 is gamma 1 and gamma 2, they are not independent of one another. So, therefore, they are more or less related to composition in this particular fashion. Next is that if we know one, we will be in a position to find the other. In what particular way we will be doing a problem and finding this out, that suppose we know one, say x1 dln gamma 1 plus x2 dln gamma 2 equals to 0. So, suppose I know gamma 1, I would like to find out gamma 2. So, what is this? dln gamma 2 minus x1 by x2 dln gamma 1, right. Now, I would like to find out gamma 2 at some particular composition x2 starting from x2 equals to 0, and here this also x2 equals to 0 to x2. So, therefore, ln gamma 2 at x2 minus ln gamma 2 at x2 equals to 0 is nothing but 0 to x2 minus x1 by x2 dln gamma 1. So, therefore, suppose I know gamma 1 or gamma 1 variation with x1, then we can find gamma 2 from gamma 1. This is number 1. Suppose we take up a problem in this respect. Say for instance, I take up a problem. I know that in a binary mixture, say suppose the problem is that I have got a binary mixture, right. In the binary mixture, I know gamma 1 is represented by a equation as ln gamma 1 equals to ax2 square, where a is a constant. Fine. I would like to find out, or I would like to express, obtain expression for gamma 2 in the same solution. So, therefore, I have a binary mixture of component 1 and 2, gamma 1 adequately represented by this particular equation where a is a constant, obtain expression for gamma 2 of component 2 in the same solution. How do we think we should be proceeding for this? Just if you look at this particular equation, we can very well find it out from here. We know that d ln gamma 1, we already know that d ln gamma 1 dx1, this is equals to minus x2 by x1 d ln gamma 2 dx1, right. This is nothing but, as I have mentioned, this is Gibbs-Duhem equation. So, from here what do we know? We know ln gamma 1, it is given, it is already ax2 square, which can be written down as a into 1 minus x1 whole square, right. So, therefore, in that case what is d ln gamma 1 dx1 equals to? It is minus 2 a into 1 minus x1, agreed. So, therefore, I know this particular term, right. So, what is d ln gamma 2 by dx1? We can simply substitute this here and we can find it out. So, therefore, this reduces to minus 2 a into 1 minus x1 equals to minus x2 by x1 d ln gamma 2 dx1. This is nothing but x2, this is also x2, and here it is minus, here also it is a minus. So, the minuses cancel out. What do I get? I get 2 a x1 is nothing but d ln gamma 2 dx1, agreed. So, I would like to find out an expression for gamma 2. So, we know d ln gamma 2 is nothing but 2 a x1 dx1, fine. We will be performing the integration from x1 equals to 0 to x1 equals to x1, right. And we know that at x1 equals to 0, what is the value of gamma 2? x1 equals to 0 means x2 equals to 1, and therefore, at x2 equals to 1, gamma 2 has to be equal to 1. So, therefore, this is going to extend from ln gamma 2 has to be 0. So, therefore, this has to extend from gamma 2 equals to 1 to gamma 2. As a result of which, if you perform this integration, what do we get? We get ln gamma 2, this is nothing but 2 into a x1 square by 2 which is nothing but equal to Ax1 square. We find that we will be dealing more with this, with such type of equations. We find that more or less, then in that case your variation of ln gamma 1 with composition and ln gamma 2 with composition, they are more or less symmetric to one another. Agreed? So, therefore, just imagine I had started from, or rather I had the expression of gamma variation with composition for any one component in a binary mixture, and we found out that since we knew Gibbs-Duhem equation, using that equation we could find out the variation of the activity coefficient of the other component as a function of composition. So, in this particular way, this is just one very typical example. You can take up a lot of examples and you will find that for most of the situations, if you know the gamma variation for one component, in whatever be the functional form, you can find out the gamma variation for the other component. This is for a binary mixture. If it is just like what I had repeated in the last class, if I am dealing with a multi-component mixture, then if I know the gammas for the n minus 1 component, I can find the gamma for the nth component using the Gibbs-Duhem equation. So, this is the first thing which is very important. The next thing, as I have already mentioned, the next thing is when we know that gamma 1 tends to 1 at x 1 tends to 1. So, therefore, we know that at x 1 tends to 1, suppose I would like to plot gamma or gamma 1 as a function of x 1. What do I know? That at x 1 equals to 1, gamma 1 also has to be 1, right. Suppose we start and suppose say there is a positive deviation from Raoult's law. So, therefore, the equation should be something of this sort. Similarly, for gamma 2, the equation should be something of this sort. What is the other thing that I know? The other thing which I know is that at x 1 equals to 1, your d gamma 1 dx 1, the slope is 0, or in other words the curve should be horizontal, or in other words we know that at this particular point when we are plotting gamma 1, the gamma 1 has to be 1 at x 1 equals to 1 and the curve has to be horizontal at this particular point. The same applies for gamma 2 at x 1 equals to 0, right. So, therefore, these are some of the important information which the Gibbs-Duhem equation provides to us, right. So, as I had already mentioned, I have also shown the plots of gamma variation with composition. If you observe these particular things, as I have told you, gamma 1 tends to 1 as x 1 tends to 1. This is true whether we have a negative deviation from Raoult's law or a positive deviation from Raoult's law. When we have a positive deviation, the value of gamma is greater than 1. So, therefore, we find that at x 1 equals to 1, gamma 1 is equal to 1. In this case also, as x 1 equals to 1, gamma 1 equals to 1, number 1. Number 2, the slope is horizontal here for gamma 1, horizontal here for gamma 2. Here also the slope is horizontal here for gamma 2, the slope is horizontal here for gamma 1. So, therefore, these are the three important, this was the first observation which we had, slopes equal and opposite. The second observation was this, and the third observation is this. And the fourth thing I have already mentioned, I have done a problem and shown you that how gamma 1, or rather how, if you know gamma variation of one component with composition, how the gamma variation of the other component can be found out. So, therefore, with this I think we have discussed sufficiently regarding the importance of gamma. Now, we have to go for finding out, and we know that this also I have repeated, we know that once we can find out gamma, then we will be able to tackle the vapor liquid equilibrium data, and gamma, as we know, it is a function of temperature, pressure, the liquid phase composition. Very importantly, which is not mentioned here, it is also a function of the vapor phase composition, because the gamma has to be obtained from this particular equation which deals with both the liquid phase as well as the vapor phase. It is important to remember that although gamma is a property of the liquid solution, in order to find it out, we need to have data on both the liquid phase as well as the vapor phase composition. Now, how to find out gamma? What are the different normal ways of finding out gamma, right? So, usually what we do is the problem types. Yesterday also I have told you that these are the different problem types, and for whatever problems are given, these are the equations which have to be used to solve them. We have already done this for ideal solution. The extra thing which needs to be done here is to incorporate the or rather is to know how to calculate gamma from known input parameters. So, well, the thing which is usually done is that, see, it is mostly gamma data, it is very difficult to find out how a real solution actually behaves, or rather how gamma in the real solution can be related to the properties of the real solution. Why? Because, see, for a real solution, when it is deviating from ideality, why it happens? Firstly, the size and shape of the molecules can be different. So, as a result of which there is a non-vanishing volume of mixing. Second thing is the intermolecular interactions, as I have said, they are different for the like pairs and the unlike pairs. So, therefore, actually if we have to find out a particular model in order to predict gamma from the liquid phase compositions, then in that case it needs a very good knowledge of the intermolecular potential, etc., and this is not very easy. So, therefore, usually the things which are done is either a semi-empirical or empirical correlations are used. Well, and these empirical correlations, they are developed from experimental data. Now, whenever you are developing any empirical correlation from experimental data, we need to remember certain things. What are those certain things? The first thing is that it must subscribe to certain limiting conditions. Number 1. Number 2 is that more or less whenever we have proposed something from experiments, it is very important to test whether it is thermodynamically consistent, and that we will be discussing later. It will be done with the help of Gibbs-Duhem equation. Now, let us see what is the easiest model which can be proposed which subscribe to the limiting conditions of a real solution and can be thought of describing the real solution behavior, or it can be related to the composition in the real solution. Usually these particular models or the equations which are proposed, they are proposed from, or rather they usually express the excess Gibbs free energy of the solution in terms of composition. What I mean to say is that in this particular case, what we do is we usually, instead of directly expressing ln gamma 1 or ln gamma 2 as a function of x1 x2, usually what we prefer to do is we would prefer to express Gibbs free energy as a function of x1 x2. Now, once this can be expressed, we know that ln gamma 1 is nothing but g1 bar E by RT, and this can very well be found out by expressing your del n1 of n1 GE by RT at constant temperature, pressure and N2, right. So, usually we try to express, or rather we try to find out activity coefficient from some particular models which are known as excess Gibbs free energy models, which express excess Gibbs free energy of the solution as a function of its composition. Why we do it? Because we really do not know that, or rather it is not very convenient to find out the limiting situation or limiting condition for ln gamma 1 and ln gamma 2. We just know that ln gamma 1 must be equal to 0 at x1 equals to 1. This is the only thing that we know. Ln gamma 2 must be equal to 0 at x1 equals to, or rather at x2 equals to 1. This is the only thing, just one limiting condition. On the other hand, when we are dealing with excess Gibbs free energy model, what do we know? We know that the excess Gibbs free energy should disappear both when either of the component is in excess, or in other words, the limiting condition in this particular case is this tends to 0 at x1 tends to 1, at x1 tends to 0, or in other words x2 tends to 1 under both these conditions. So, therefore, the simplest expression which expresses the excess Gibbs free energy in terms of composition should become equal to 0 either when x1 becomes equals to 0 or when x2 becomes equals to 0. So, therefore, what can be the simplest expression? Simplest expression can just be this, a product of the compositions where A is a parameter which has to be determined experimentally, and this particular equation which is the simplest Gibbs free energy model, this particular expression it is known as 2 suffix Margulis equation. And here I have shown you that for this particular condition, what should be the characteristic of the Gibbs free energy, the excess Gibbs free energy as a function of composition, and the characteristics of ln gamma as a function of composition. If you observe, you find that in this particular figure we find that G by RT it is symmetric about 0.5. Why? Because we have taken A equals to 1 in this particular case, right, and this shows the corresponding variation of gamma 1 and gamma 2 as a function of composition. Just note the difference with the previous curves which I have shown you. The previous curves it was just gamma versus x1, as a result of which we have obtained curves of this sort. In this particular case it is ln gamma versus x1. So, therefore, we find that ln gamma reduces to 0 at x2 equals to 1, ln gamma reduces to 0 at x1 equals to 1, right. So, therefore, we find that the simplest equation which can be used in order to find out the excess Gibbs free energy is nothing but the simplest expression is the product of the two compositions, and from here if we find out the expressions for ln gamma 1 and ln gamma 2, which as I have told you we can find it out from this particular expression. We find that in this case ln gamma 1 equals to ax2 square, ln gamma 2 equals to ax1 square. So, this is the simplest equation, and this is, and for this particular equation we find that while for A equals to 1, while G by RT is symmetric about x1 equals to 0.5, we find that the activity coefficient curves, they are mirror images when ln gamma is plotted against x1. And this particular parameter A, this can be 0 when it reduces to an ideal solution, that this can be greater than 0 or this can be positive, which signifies G by RT is positive or a positive deviation from Raoult's law. This can be negative, which signifies a negative deviation from Raoult's law. And this particular equation, which is known as the 2 suffix Margulis equation, as I have as has been mentioned here, this particular equation we find this is quite accurate, or it is adequate to represent the behavior of liquid solutions when the components are of similar shape, the similar size and similar nature. And for such cases it is good, but for most of the situations we find that the case is slightly more complex and we need to modify the simplest expression which we have shown in order to predict the behavior of slightly more complex liquid solutions. We are going to deal with it in the next class.